Welcome back to my channel, InfoSec Lab. Today we're going to talk about HTTP Browser Desync, another vulnerability in HTTP Request Smuggling. Now, this is a part of series web app pen testing from TryHackMe. Let's get started. Introduction. Request smuggling traditionally focuses on issues within the communication between front-end and the back-end servers, or between the back-end servers in a proxy or load balancing setup. The attention may not have been extensively directed toward understanding how these vulnerabilities manifest and can be explicitly exploited in how web browsers interpret and handle these smuggled requests. Desynchronizing the interpretations of requests within browsers adds a layer of complexity and opens up new possibilities for exploitation. This technique necessitates only the synchronization of the front-end server, impacting the victim's connections with their browsers. Objectives. First, we have to understand what HTTP Request Browser Desync is and its impact. Then we identify the browser HTTP request smuggling vulnerabilities in web applications and learn how to exploit this vulnerability in a controlled environment. There are some prerequisites for the room. First, a strong understanding of HTTP protocol, some prior experience with the traditional request smuggling techniques in precise context, and an understanding of client-side attacks is foundational. Let's talk about HTTP features. HTTP Keep Alive. HTTP Keep Alive is a mechanism that allows the reuse of a single TCP connection for multiple HTTP requests and responses. It helps reduce latency and improve performance by avoiding the need to open and close connections repeatedly. However, it can introduce a security risk known as cache poisoning. If caching mechanisms are in place, the persistence of connections through Keep Alive could contribute to cache poisoning attacks. An attacker might exploit desynchronization issues to store malicious contents in caches. HTTP pipelining. Usually with HTTP, one request results in one response. If the HTTP pipelining is enabled in the backend server, it will allow the simultaneous sending of two requests with the corresponding responses without waiting for each response. The only way to differentiate between two requests and a big one is by using the content length header, which specifies the length of each request. The content header is an unnecessary header for most static file contents in web applications, like images or icons, since the backend server will usually not consider it. Answer the question. Which HTTP features allow you to send multiple requests at once? Pipelining. Which HTTP feature allows you to reduce TCP connection for multiple requests? Keep Alive. Now let's talk about HTTP Browser Desync. HTTP in a browser desync attack. The attacker aims to take control of a victim's account by exploiting vulnerabilities in the web application's user connection system. The attack occurs in two steps. First, the initial request, appearing legitimate, is intended to disrupt the user request queue by introducing an arbitrary request. Once the connection pool is compromised, the next valid request will be replaced by the arbitrary request initiated in the previous step. Let's take a look at the high-level representations of the attack. First, the client initiates a POST request utilizing the Keep Alive feature, ensuring the connection remains persistent. This persistence allows for transmitting multiple requests within the same session. This POST request contains a hijack GET request within its body, which is this one. If the web server is vulnerable, it mishandles the request body, leaving this hijack request in connection queue. When the client makes another request, the hijack GET request is added to the forefront, replacing the expected behavior. In this scenario, attempting to access the redirect page automatically will show the output from the 404 page instead of the redirect one. Answer the question. Which component is desynchronized during this attack? Browser. How many HTTP requests are sent during a browser desync attack? So we have 1, 2, 3. HTTP Browser Desync Identification. For a better understanding of HTTP browser desynchronization, we will use a web application vulnerable to CVE 2022-29361. The web app will serve a single route. To execute the attack, a straightforward approach is to utilize the fetch JavaScript function. This function allows for maintaining the connection ID across requests. The connection ID refers to a unique identifier assigned to the network connection between the client and the server. This identifier helps the server keep track of multiple connections and distinguish between them. This consistent connection ID lies in its ability to facilitate exploitation for an attacker that could expose user information or session tokens such as cookies. Moreover, in a cross-site attack, the browser shares user cookies based on how the same site flag is set, or CORS. But this security rule doesn't apply if the current domain matches the remote one. As in browser desync attack, in such cases, there's no restriction. You can hack your sessions by using the following payload from your browser command line. So let's dive into this payload. This is going to be the URL which the HTTP request is made for the vulnerable server. In this case, it's a registration endpoint on the local server, and it's using the post method. Here's the body of the post method. Which is the hijack get request. It's flag that triggers an error when visiting the 404 page and avoid following the redirect. So let's start a virtual machine. The vulnerable website will be running on port 5000. Furthermore, this implies that an attacker can obtain complete control over a victim's browser when the specified payload is executed from the victim. The following screenshots will show an example of the attack using the previous payload. And now we're going to copy this payload, the fetch request, paste that into the console, allow pasting. The desync attack involves injecting an arbitrary request into the request HTTP queue. Upon refreshing the page, it redirects to the redirect endpoint, leading to a 404 error page displayed since that route is not present. So now we can refresh the page and we get a 404. That's expected. So that's how we identify the browser desynchronization. So which JavaScript function can help to perform the browser desync attack? Fetch. Which security mechanism is bypassed by the browser desync attack? CORS. HTTP Browser Desync exploit chaining with the XSS. Based on the considerations outlined in the previous task, one potential attack vector involves replacing the following request with an arbitrary JavaScript file is to execute custom code. However, this strategy necessitates the presence of an arbitrary file upload feature on the website. Instead, we can use a rogue server to deliver an XSS attack to steal the cookie from the victim. We can use the following gadget and deliver it to abuse any component on the web application that allows to reflect text and probably be visited by a user. We utilize a form because it inherently supports a keep alive connection by default. The type is used to avoid the default encoding MIME type since we don't want to encode the second malicious request. Furthermore, the text error's name attribute will override the bytes of the following request, enabling redirections to our rogue server. To summarize, this gadget operates by using the initial request to position the victim within the connection context of the vulnerable server. The following request retrieves the malicious payload, compromising the victim session. To do so, we can set up a rogue server by serving the route to malicious payload. Answer the question. This technique can be combined to a browser desync to steal a user section XSS. Okay, so let's go to the challenge. We have a challenge.tsm right here. These are the steps. First, we have to identify the current web server is vulnerable to the client-side desync. Then we have to find a functionality that allows us to store a malicious gadget. And we have to build our malicious payload for the session takeover. We combine everything and still use this cookie. First, we're on the home page. As you can see, it will try some random value. Obviously, it's not working. We try to sign up. Nothing happens. So if we try help, we have two fields right here. So I just want to make sure that I don't miss anything. I'm going to deliver this to payload. And submit it. Now when I click this URL, it takes me to a secure contact. From here, I can make a guess that there's also another directory which is vulnerable contact, and I was right. The XSS payload reflected on this endpoint. So now we have successfully identified the current web server is vulnerable to the client-side desync, and we also found a functionality that allows us to start a malicious gadget. What's next? We have to build a malicious payload and then build our server. Let's go with our payload first. Over here, we can copy this one. We use a form. Now my test, and we're going to paste the form right here. This one will replace with our IP address, which is 10.64.121.54. 121.54. Let's do it on port 5555. And we save it. Over here on our terminal, we're going to set up our server, and here's our code. Because we directed the user to port 5555. Over here, I set the default port on 5555. Basically, what this script does is, whenever there's a connection made to our server, it will respond with 200 status code with the following headers. It also fetches a request to our rogue server where we can steal the user cookie. Now this one is going to be on our web server too, on port 8080. So let's save this one, and yes. So we have to run two servers. First one is this one, the server.py. And then second one is going to be HTTP server on port 8080. We're gonna have to wait for a few minutes, and then after that, we're going to get the user's cookie section. And there we go, we got a flag. TryHackMe smuggler is fun. Alright, so that's it for the room today. Browser desync represents a relatively recent and severe security threat in web applications, exploiting how servers handle HTTP requests. This attack relies on inconsistencies in how servers interpret request bodies during continuous connections, allowing attackers to manipulate subsequent requests for malicious purposes, like cross-site scripting. This room is pretty straightforward. However, there's some little details that may be confusing to you, so don't worry if you get confused at first. If you have any question or concern about this room, feel free to reach out to me, and then I will help you to help. Now with that being said, I'll see you next time. Thank you again for watching my video. See you. Bye.